Okay, now let's continue from here. We just say like, okay, the length that the observer from the spacecraft see the space station is not as long as its original length. The proper length is 1,200 meters, but anyone on the spacecraft could see it as really short, just 720 meters. But actually, that's not the distance between the light pulses. So why? Okay, and actually, if you check the mark scheme, they provide that we can use this equation, the Lorentz transformation. So let's see how this Lorentz transformation work in details, and I will show it to you in the very next pages with a lot of more details. But before move on, I want to highlight these things. Here, proper means reference of the space station. We are kind of on the read, right? And we also see that the thing is that they're talking about the distance between the light pulses. So for someone at the space station, they see that, okay, at the rear, at the front of the space station, R and F position, the two beacons, the two pulses, boom, at the same time, right? Nothing different. But for the spacecraft, some person in the spacecraft, they don't happen at the same time, right? Remember about the concept of time dilation? Okay, so like the proper times here at the space station is 0, but for the one from the spacecraft, it's not 0, they're different. So because they're different, so that's why the length is not this one, right? It's not, they're not asking for like how the proper length is visual flies from the spacecraft, because we're not talking about the two events happen at the same time. That's the key, and that's why we need to like stick with the Lorentz transformation. So actually, I don't understand how and why they mentioned that allow use of this length contraction, or like even allow use for the time dilations in here. To be honest, I don't know. I haven't figured it out yet. So if you happen to know, please let me know and teach me about it, but I don't know. So here, I just want to focus on how to use the Lorentz transformation, and how it's like the key thing is like why we cannot use this equation. Okay, so this is the details. Here, this is the space station, and I would choose the positive direction for the position to be in this direction from left to right, because as in the problem statement, the spacecraft is like moving to the right, so that's why I just want to have the V as positive, to make the math easier. So as I choose this one as positive direction, and we can see that the spacecraft is moving in this direction, that's why the V has a positive value. Remember the thing that I mentioned in the previous video, V have to be based on the reference A, okay? We are going from reference A to reference B. So this is the Lorentz transformation. We have figured out the gamma factor, the Lorentz factor, to be 5/3. Just plug in the values. And yeah, if you want me, I can just note it down here, because we have, it's just here. V over C just like 0.8, right? Because this is from the problem statement. So just plug in this 0.8 into this one, square it, y minus that square root it, and then inverse it, then you got 5/3. Okay, so basically, if I call the event 1 when the pulse is emitted at that position R, I would assign XR to be 0. Then XF just automatically will be 1,200 meters, right? Because it's like 1,200 meters away, and in the positive direction, so it's this value. They happen at the same time, so why not just choose them to be 0, right? Easy. Then from this, we got XR, TR. Then you just plug in those into this equation. You can find the XR in the reference frame B and TR in the reference frame B. Easy, right? So gamma 5/3 times what? That's 0 just to be 0. And the same T just like 0. Okay? So for XR prime and TR prime, it's just like the same, 0 to the person on the spacecraft. Okay? So it means that the pulse will emitted is looks being emitted at the R position of the space station at the time point 0 and at the position 0 compared to the person on the spacecraft. Okay. What about the F? Just do exactly the same thing. Just plug in the values in here, SF into here, here, TF into here, here. Then you can find that XF prime is 5, 5/3 of that values. Then it should be like 2000 meter. And then the T prime, just plug in the values here. This is 0. Then just this one left, and then just add in. And because you see, this is positive and this is like negative, so TF to be negative. Okay, so here we usually know that time should be positive, so can time be negative? And yes, it is, because here we don't talk about the time interval, but we are talking about the time point. So time point can be fairly to be negative or positive. It just depends on at which point you assign it to be the 0 point, okay? So basically, you got this one to be negative. And that's the key. Why? Because if this one is negative and at the R is 0, it just means that event 2 occur first. Okay? It's occur first to the person on the spacecraft. That's why it's less than this one. So basically, for the people on the space station, they see the pulses emitted at the two positions at the same time, 0. But for the people on the spacecraft, they not happen at the same time. They happen at first. It just happened that way to them because they're moving so fast. And that's why these measurement, these coordinate of X and F is not at the same time. That's why we cannot apply the length contraction in this case. Does it make sense? Right? Okay. So that's about when you want to go from reference A to reference B. And then that's also how the mass scheme really doing. And they just like combine these two. So instead of like writing XF, XR, they just got this one just like XF prime minus X R prime, something like that. Then they can have a like simpler look of the equation, but I just want to make everything really explicitly to you. So that's why I go into that much details in here. So we can see that this is basically what the mass scheme did to get that values, okay? And I want to explore a little bit more. So for you can see that it's just a reminder, you can either go from this reference to this reference, or you can go the other way. You just have to get the right V, the right value V to plug in. So what happened here? I tried to redo the problems from another way. Of course, this is not complicated, but it should agree with the result, okay? So basically, compare to the spacecraft. The space station seems to travel in the opposite direction, right? Right? Just like when you're on the train, you see that the trees are moving backward compared to you, while you are moving forward compared to the trees. Okay, this is the same thing. So for the person on the spacecraft, the space station seems to move to the left. Basically, that's way. And because we also assign the same positive to be like the right one, then this V here becomes negative. Okay, it turns to be negative, and just keep that in mind when we need to plug in the values here. And actually, I just want to go this way because I'm just curious if it's correct, And you can also see that it's pretty interesting that even if you go from this frame to this frame, you also have gamma multiplied with it. But if you go to the other way, you also have gamma multiplied with it. Gamma is a very special factor, okay? And there's a story about it. If you want, we can talk about it in another video, but not now, okay? Let's get back to the point here. So actually, we want to looking for this one and looking for this one. And remember, we have two variables to solve. So as long as we have two equations, then we can have a system of equations that we can solve for it. And basically, just plug in the values in here. You have a system of two equations. Equation 1, I just basically plug 0 meter here into here, and then just rewrite these things here again, and equation 2 here, and then just rewrite everything again, right? And just do solve these problems based on substitution. I could say that you're kind of familiar with this, right? Basically, I will try how to express tr prime according as in terms of x r prime, and then plug a whole things here into this one here. Then see into equation 1. Then it just becomes an equation of one variable. And from here I can find this. Easy, right? And then just do the same thing. You can check the math I'm doing right here. But basically, after solving this one, I found that x prime f to be 2000 meter. Same result. And then just like come back here to plug in here, I can find the t prime of f to be same, right? So I just want to highlight to you that it doesn't matter if you go from frame A to frame B or frame B to frame A. As long as you have the correct V identified, then you can just do the Lorentz transformation in any pairs of preference. Okay? Okay, so that's it for the details of working out this one. And then in the next video, I will summarize everything with a diagram, a figure for you to easier to visualize it. So let's just I go say that I recommend check out the last part of this explanation. Okay, that will be part 3. Okay, see you soon.